Welcome to Spring LIB.
In this exercise, we're going to be working with the concept of force. And in order to solve the problem, first, I'm going to briefly review how we deal with force. So according to Newton's second law, we have that F, that is the sum of the forces that act on a body, so I'm going to write it as a sum of the forces, is equal to the mass of the body times the acceleration. And this is what we're going to need in order to solve our exercise. So in our problem, we have two blocks, one of mass MB, block B, and the other one of mass MA, block A, that are positioned as shown here in the picture. Both blocks are shaped like a right triangle and placed on top of one another. And the angle here of block B is theta. And a certain force P acts upon block B such that the two blocks move together. And our goal is to find what is the value of P. The exercise actually asks us to find the largest value of P that will result in the two blocks being stuck together. So that will result in block A not moving relative to block B. Okay, so how do we do this exercise? What we need to do first is to draw the free body diagram for both blocks. So first for block A, here, the forces that act on block A are the gravitational force that acts downwards and has a magnitude of MAG. Also, the normal force that block B exerts on block A, that is perpendicular to block B, and I'm going to call that force N prime. And these are the only two forces that act on the block. Remember that this here is theta, so this means that this angle here is theta. Okay? Also, we have block B, and the forces that act on block B are the P force, the gravitational force, MBG, the normal force that block A exerts on block B, which is N prime according to Newton's second law, since the force that block B exerts on block A is the same force that block A exerts on block B. And also there's the normal force that the ground exerts on block B, which I'm going to call just N. So given this, we are in a position to write the equations of motion for blocks A and B. And I'm going to set up a coordinate system such that the y-axis is pointing upwards and the x-axis is pointing to the left. So first for block A, we have in the y-axis that the y component of the normal force is N times cosine of theta. Then we have MAG, and this is equal to 0 since the blocks are not moving in the y direction. And in the x component, we have N times sine, actually this should be N prime, I'm sorry. N prime times sine theta is the only force acting in the x direction. And this is equal to the mass of block A times the acceleration. And the acceleration of block A and block B is the same, and I'm calling it A. For block B, we have in the y direction N acting upwards. Then we have minus N prime times cosine of theta minus MBG, and this is equal to 0. Then in the x direction, we have P minus n prime times the sine of theta, and this is MBA. Okay. Now notice that from the equation for the y coordinate for block A, we have that n prime is equal to MAG divided by the cosine of theta. And if we plug this into the equation for the x coordinate, this one, we have that G is equal to A times the cosine of theta divided by the sine of theta. So A is equal to G times the tangent of theta. And then we can look at the equation for the x coordinate for block B, and we have that P is equal to n prime times sine of theta plus MBG. Okay. Now n prime times the sine of theta is MA times the acceleration. And I'm sorry, this shouldn't be G, this should be just A, the acceleration, plus MB times the acceleration. Now the exercise tells us that MA and MB, the two masses, are the same and they're equal to M. So P is equal to 2 times M times A. So this is 2 mg times tangent of theta. So P can only actually have one value, and the only value it can have is 2 times m times g times the tangent of theta, which concludes our exercise.